Hello class, today we'll be going over nucleophilic aromatic substitution. So first I want to review the pair that is normally talked about most between the two, and that's electrophilic aromatic substitution. So with a quick review, the benzene ring acts as the nucleophile with the double bonds acting particularly as the nucleophile, attacking electrophile. And with that we have this intermediate with this carbocation intermediate, in which once the electrophile is bonded, and we have this tetrahedral carbon here. With that, a base normally comes along and takes the proton with the electrons from that bond between the carbon and the hydrogen, going to the benzene ring and restoring the aromaticity. And with that, we have the attachment of the electrophile with the proton acting as the leaving group. So the substituents for electrophilic aromatic substitution act as directing groups. So depending on which substituent you have, it will increase the amount of product you'll have, depending on the type of product you'll have. So with electron donating groups, it'll be you'll have more substituents or products with substituents at the ortho and para position. So with electron withdrawing groups, you'll have them more at the meta position. So with the benzene ring acting as the nucleophile, you'll want a greater electron density to attack the electrophile. So electron donating groups tend to be the best. So these also tend to increase the rate. As well, for the electron donating group, it will increase the it will increase the electron density at the ortho and para positions. So, or the electronic effects when you put a substituent on the benzene ring normally affect the ortho and para positions, whether that be decreasing or increasing electron density. So with this being nucleophile, or the benzene being the nucleophile, the greater electron density the better. So the electron density with the electron donating groups is at the ortho and para positions. So these are more nucleophilic than the meta positions. But with the electron withdrawing group, the effects are still ortho and para, but that's a decrease in electron density. So these are more partially have partial positive charge in comparison to the meta groups. So it's not that the meta groups get an increase in nucleophilicity, but rather that the ortho and para get a decrease. So, and this also tends to decrease the rate since you're withdrawing the electron density away from the nucleophile. So just a quick summary, the double bond of the benzene ring is acting as the nucleophile. There's a carbocation formation. The substituents act as directing groups. Electron donating groups tend to increase the rate because this is a nucleophilic attack of the benzene ring. And the rate determining step is the nucleophilic attack. So now we are actually going over the nucleophilic aromatic substitution. So this is also a two-step process, an addition-elimination reaction. So with that, we have the nucleophile attacking the carbon in which the leaving group is attached. So this forms a carbanion, not a carbocation, but a delocalized negative charge. As well, there is a tetrahedral formation where the nucleophile bonds where the leaving group is. So, and this forms an intermediate, and this intermediate is stabilized so much so that we're able to isolate that, but go over that in a minute. But this is generally called the Meisenheimer intermediate. As well, the first step with the nucleophile attacking the carbon with the leaving group attached is the rate determining step, which becomes important a bit later. And step 2 is the elimination, similar to similar to electrophilic aromatic substitution. We have an elimination in which a leaving group is taken off. But in the first one, it was more removed, where here it is just taking off. So here, the delocalized electrons reform a bond, pushing this bond off here toward and connecting to the carbon that already has 4 bonds attached to it. So carbon can't have 5 bonds in these cases. So the electrons between the leaving group and the carbon, they go towards the leaving group, and the leaving group leaves, leaving only the nucleophile attached to where the leaving group is. So step 2, the elimination. Generally, this is where the heat increases the rate. Most of all, heating is often necessary for this step. So if it's too cold, it won't continue very much. More depending on this step than this step. So also this restoration of the aromaticity is part of what drives this reaction forward to become more thermodynamically stable at this stage. So leaving group eliminated, aromaticity restored, and heating often necessary. So a little bit about the substituents. So unlike the electrophilic aromatic substitution, where the substituents are directing groups, here they are not directing groups. So they are not affecting where which carbon the nucleophile or the other molecule will attach, because they're always going to attach at the carbon with the leaving group. So they affect the rate, but they don't act as directing groups. So with electron, you'll want electron withdrawing substituents on your ring, because this is the ring is acting as the electrophile. So the more electron deficient, the better, and so the more likely the nucleophile will attack. And you'll especially want it at the, let's see here, okay, yeah, you'll especially want it at the electron deficiency to be at the carbon where the leaving group is attached. So normally you'll have them ortho and para to the leaving group, because the electronic effects, whether electron donating or electron withdrawing, the effects are generally at the ortho and para positions. So if you want electron density decreased, you'll want ortho and para positions to be taken up by your substituents. So this increases the rate. If you have it at the meta position, this decreases the rate in comparison to the in comparison to having the substituents on the ortho and para position, because instead of having this carbon being more electron deficient, where the nucleophile will want to bond to it more strongly. Let me fix that to get that on screen. Instead, it's being wasted on the other carbons that are ortho para to it. So you don't want your substituents on the meta locations. Let's see. So here, once the nucleophile is attached, the electron of the carbanion is formed, but it is delocalized around the benzene ring, which is why benzene is able to act as electrophile, because this carbanion formation is stabilized by this resonance. In fact, these these intermediates are so stabilized that we're able to isolate them. So Meisenheimer was a chemist who helped prove this reaction mechanism for this reaction, because he was able to isolate these intermediates at very low temperatures. So so the resonance stabilization allows for this to take place. As well, the while electron withdrawing groups decrease the electron density around the ring, increasing its electrophilicity, the resonant withdrawing groups especially aid it, because these groups are able to participate in the stabilization. So because this benzene ring is able to stabilize the delocalized electrons, this helps the reaction take place. But if you're able to further increase the aromatic system, this just further increases its stabilization. Let's see. Oh, also, while nitro groups are generally what you'll see most often, other resonant groups such that have double bonds, generally like carbonyls, could also be used. Though that gets a bit more tricky because sometimes the nucleophile will tend to attack them instead of the benzene ring. So just a little bit about the leaving groups. We have generally what you'll see in textbooks and online is halogens being used as leaving groups, and the reaction rate actually increases with greater electronegativity, which was different than for electrophilic aromatic substitution. And so much so that you'll see fluorine even being used as a leaving group, which generally for SN1 and SN2 reactions, you never have fluorine as a leaving group. But in this case, it is actually the best leaving group of the halogens. And this is partly due to, instead of the leaving group leaving being the rate determining step, it's actually the nucleophilic addition, which is the rate determining step. So it doesn't quite matter how bad the leaving group is, or how long it would take for it to leave, or for enough of the molecules to react to have it to where the fluorine ends up as the leaving group, because it doesn't really matter how slow it is, step 2 is, because it'll always be much quicker in comparison to step 1, which also allows for alkoxy groups to act as leaving groups. But as well, with the greater electronegativity in the leaving groups, these still will aid in increasing the electrophilicity of the benzene ring. So just as the substituents are doing that, so can the leaving group. So fluorine, being the most electronegative atom, just further increases the rate to a much higher order than the other three. As well, you're able to use alkoxy groups as leaving groups for similar reasons, or for similar reasons for the rate determination, not exactly for the electron withdrawing capability. So for the nucleophiles, just a few quick facts. Generally, you need strong nucleophiles for this type of aromatic substitution, because this type of substitution is more specialized. You won't see it as often as electrophilic aromatic substitution. So generally, because you'll need very specialized conditions. So generally, you need strong nucleophiles, usually things with a negative charge on them, as well as a few different amine groups. And the nucleophile must be a stronger base than the leaving group. This especially plays a role whenever you want to replace alkoxy groups, say with this methoxy to this ethoxy. The only reason this is able to take place is because this ethoxide would be a stronger base than the methoxide here. Otherwise, this wouldn't take place. So, just a quick summary. We have an addition-elimination mechanism where benzene acts as the electrophile, and electron withdrawing groups are necessary for ring activation, especially if they are able to participate in the aromatic system, or the resonance, able to participate in the resonance. And there's a carbanion intermediate that is formed, so much so that is stabilized, that it's isolatable, and it's stabilized by this resonance of the benzene ring, as well as sometimes the substituents attached. So we have the background covered. So now we are going over the experiment. So we didn't get to do an experiment in class, so I'm going over a theoretical one here, the one that we would have done, the synthesis of the 2,4-dinitrophenyl thiocyanate. So we have our normal reagents that we'd be using, our starting material, the 2,4-dinitrobromobenzene, as represented here, as well as its solvent, toluene. We have, we have the potassium thiocyanate salt in a aqueous solution, And because we have a organic solvent, an organic layer, and a aqueous layer, but each one holds a reagent that needs to combine and react, we have a phase transfer catalyst that you may be that you will be familiar with, tetrabutyl ammonium bromide. So I have it represented here. So we have our organic layer with our toluene solvent and a representation of our starting material. Obviously, these aren't to scale, two different benzene rings, as well as our salt in our aqueous solution, and even our carborundum granule with bubbles forming. So we have our carborundum granule, the most important part, because even if you leave out a reagent and you just don't get a reaction, it's always better than heating up a solution with no way for the gas to escape. We have 3 mils of dichloromethane, which we'll be using for extraction, as well as the DI water, chloroform D for the NMR, and the purification, as you're familiar with, silica gel and anhydrous sodium sulfate. So our normal setup would look like this, where we have we're heating this up and refluxing. So we will have a water jacketed condenser for cooling, and as normal, the water flows in through the bottom, out through the top, and we'll be using our 5 mil conical vial. And we have the attachment here, and of course all this will be underneath, or part of this will be underneath the sand heating up, and this will all be held by our clamp. So once this is, so we would be adding these 4 in together and heating it up. And during that reflux, we will have this reaction take place, in which the thiocyanate nucleophile attacks the carbon with the bromine attached, forming our intermediate. And eventually, this resonance stabilization allows for this intermediate to exist, but it will want to reform and reshift these double bonds back to its aromatic ring on the benzene, pushing off the bromine, with the bromine acting as the leaving group. And so we'll have our bromine ion floating in solution, as well as our final organic product. So after we would let it cool and take it off, we'll take it off the heat, let it cool down, then we'd move on to the extraction. So we have our toluene layer here up on top, and our water layer on the bottom, with water being denser than toluene. So this will be a little bit different, in which we'll extract the toluene first, before adding a more organic layer to make it easier to extract, because we're only dealing with 0.6 of a milliliter. Because we're adding dichloromethane, which is heavier. Oops, please excuse that alarm. We're adding dichloromethane, which is denser than water. So the water would then be the top layer after the extraction and the addition. So with that, we'd have a cap, shake, and vent, and we'd shake it up, in which any organic product left in the water layer will have moved to the dichloromethane layer, the organic on the bottom, and we'd extract that out and collect that in with the toluene, in which we do that twice. So it's generally not good practice to add, if you have 2 different layers, aqueous and organic, to add organic that is both heavier than your aqueous layer, dichloromethane, and lighter, because that would make the extraction more difficult, because the densities would get closer together, in which you would have you'll have like an immiscible layer. It would be very difficult to separate out. So after we have our organic layer, there's probably still some water in it, so we'll need to dry that, as well as a possibility, I guess I can draw that out, where whenever the organic shifts over, it's possible that we'll have a little bit of the salt located in our organic layer. So the sodium sulfate will help dry it, as well as the silica, which can also act as a drying agent, but not as well as sodium sulfate, as well as the silica, being very, very polar, will stop any salts left in the organic layer in its tracks. And of course, we have our cotton inside the pipette, just to keep everything from running out, but allowing the liquid to go through, and we would be collecting it in our round bottom flask, rotovapping it, and obtaining our solid, obtaining our solid product. In which case we would take out a milligram or two, add the chloroform D, and run an NMR. So likely our NMR will look like this. So the only hydrogen that we'd have to analyze would be, for our proton NMR, would be here, here, and here, with no other hydrogen located on this structure. And with it being a benzene ring, we only have one at each location. So all these won't be equal, as you can see. So with these electron withdrawing groups, with thiocyanate acting as a weaker electron withdrawing group than the nitro groups, all these are very de-shielded. So the protons have electron density around them, but the less electron density they have, the more exposed they are in the NMR, the more de-shielded they are, and the further down they are to the higher ppm numbers. But so with these very strong electron withdrawing groups, they are very de-shielded. Excuse me. But this hydrogen here, located between two nitro groups, will be the most de-shielded, and this is represented by this one big singlet peak here. As well, it has no neighbors, so it will have no splitting, so will only be represented by a single peak, a singlet. These two here have neighbors, or are each other's neighbors, so we'll have two doublets. But one is further de-shielded than the other, because the nitro group is stronger, has a stronger withdrawing than the thiocyanate group. So it takes on more of the electron density and pulling it away from this hydrogen more than the thiocyanate group would for this hydrogen. So it is the hydrogen that would be located here. As well, I have the NMR for the starting material, because if your experiment didn't go all the way to completion, then it's likely that you wouldn't have it's likely that you'll be seeing some of your starting material show up in the NMR as well, because it would make it through the purification process. So it's still this, and this hydrogen, but with only the leaving group here being switched out. So it looks very similar, but in this case, the proton here would be a bit more de-shielded, with bromine being I believe a stronger, being more electron withdrawing than the thiocyanate group. So these two would be a bit closer together, and likely if we put it on our 90 megahertz NMR with, say, only 8 scans, it's likely that these would be very close or on top of each other. So you may see, but with it going to near completion, with only a little bit of this being here, it's likely that you'll just get an NMR looking like this, with maybe the integration for this one being a bit stronger, because these two would be right on top of each other. So it would be these peaks here being just a little bit bigger than these here. So thank you for listening, and I hope you have a good rest of your day.